Every detail in this story comes from real scientific research and observation. There is a place between Mars and Jupiter where the solar system keeps its oldest secrets. Not a planet, not empty space, something in between. A belt of rock and ice and metal stretching across 280 million kilometers of orbital path, containing more than 1 million objects large enough to be tracked, and billions more too small to name. One of them is round. That should not surprise you, but it does. In a region full of jagged, irregular, tumbling fragments, one object pulled itself into a perfect sphere. It used its own gravity to do it. It separated its heavier material downward and its lighter material upward, the way a planet would. It may have built a layer of ice beneath its surface, possibly holding more fresh water than exists on all of Earth. It was discovered on the first day of the 19th century. The astronomer who found it thought he had found a new planet. He named it after the goddess of the harvest. He watched it move against the stars for 41 nights before illness took him away from his telescope. By the time he recovered, it was gone, swallowed by the sun's glare. Other astronomers found it again, then they found more objects nearby, then more. Within 50 years, what had been called a planet was reclassified. Not a world, a rock among rocks. The name stayed, the status did not. For 200 years, it sat in the dark between worlds, neither visited nor understood. Then a spacecraft arrived. It came on a beam of ionized xenon gas, pushed by the gentlest engine ever built for deep space travel. It traveled for more than 7 years. When it finally slowed into orbit, it began sending back photographs that no one had fully anticipated. Bright spots. Inside a crater 60 miles wide, 2 points of light blazed out of the darkness, brilliant white, surrounded by shadow. They should not have been there. The models did not predict them. The leading theories required revision. What the spacecraft found was not ice. It was salt, specifically sodium carbonate, the kind of mineral that forms when liquid water evaporates near the surface of a rocky body, which meant the water had been there, which meant it might still be there, somewhere below. A dwarf planet, a remnant, a leftover piece of something that never became what it was trying to become. And underneath its cold, cratered surface, the data suggests something unexpected is still happening, something warm, something that has not finished yet. You are going there tonight. This is quiet science at bedtime. If this is your kind of story, a subscribe means everything right now. Every detail in what follows is grounded in real scientific research and peer-reviewed observation. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. Between the orbits of Mars and Jupiter, at distances ranging from 2.2 to 3.2 astronomical units from the Sun, there exists a structure that most people imagine incorrectly. When you picture the asteroid belt, you probably see something dense, a narrow corridor packed with tumbling boulders, dangerous to navigate, the kind of obstacle a spacecraft must carefully thread. That picture comes from science fiction. The reality is almost the opposite. The asteroid belt is by volume nearly empty. It spans a region of space so vast that if you were to stand on any given asteroid and look around in every direction, the nearest neighboring object would most likely be invisible to the naked eye. The average distance between tracked asteroids is roughly 1,000,000 kilometers. The total mass of everything in the belt, every rock, every metal chunk, every icy body, every grain of dust, adds up to approximately 4% of the mass of Earth's moon. If you gathered every object in the asteroid belt and compressed it into a single body, it would not be large enough to be considered a significant moon by the standards of this solar system. That emptiness is not an accident. It is a consequence of something that happened more than 4 billion years ago, when the solar system was still assembling itself from the disk of gas and dust surrounding the newly ignited sun. In the region we now call the asteroid belt, solid particles were beginning to do what solid particles do in the early history of a planetary system. They were colliding. They were sticking together. They were building larger and larger bodies through a process called accretion, the same process that built Earth, Mars, Venus, and every other terrestrial planet in the inner solar system. The material was there. The conditions were right. But there was a problem. Jupiter was forming at the same time, approximately 5.2 astronomical units from the Sun, just beyond the outer edge of what would become the asteroid belt. Jupiter did not form slowly. It assembled its enormous core of rock and ice rapidly, perhaps within a few million years, and then it began accumulating gas from the surrounding solar nebula at an accelerating rate. By the time the planet we now know as Jupiter reached something close to its final mass, approximately 318 times the mass of Earth, its gravitational influence extended far inward across the entire asteroid belt region. What gravity does to a disk of debris when that gravity is strong enough and close enough is not simple. It creates resonances. A gravitational resonance occurs when the orbital period of a smaller body forms a simple mathematical ratio with the orbital period of a larger one. When that happens, the smaller body receives repeated gravitational nudges from the larger one at the same point in its orbit each time it comes around. Those nudges are small individually. Accumulated over thousands or millions of orbits, they are not small at all. They push the smaller body's orbit into increasing eccentricity, stretching it from a circle into an ellipse, and then into a wider and more chaotic ellipse until the body is eventually flung away from that orbital zone entirely, ejected either into the inner solar system or outward beyond Jupiter. You can see the evidence of this process today if you look at the structure of the asteroid belt with precision instruments. There are gaps, not metaphorical gaps, actual voids in the asteroid population, regions where, statistically, almost no asteroids orbit at all. These are called Kirkwood gaps, named after the American astronomer Daniel Kirkwood, who identified them in 1866. The most prominent gaps occur at orbital periods that are exactly 1/2, 1/3, 2/5, and 3/7 of Jupiter's orbital period, at a distance of 2.5 astronomical units from the Sun, where an asteroid would orbit the Sun exactly 3 times for every 1 Jupiter orbit. There is almost nothing. The resonance cleared it out. The same is true at 2.82 astronomical units, where orbits fall in a 2-to-1 relationship with Jupiter. These are not empty by coincidence. They are the visible record of 4 billion years of gravitational sculpting. What remained after Jupiter finished its work was not a failed planet. It was the debris field of a process that was interrupted before completion. The material that stayed in stable orbits between the resonance gaps, the material that Jupiter's gravity never quite reached with enough consistency to eject, that is the asteroid belt. It is the leftover particles of what might have been a planet, preserved in roughly the orbits they occupied during the early solar system, changed by collisions and slow orbital drift, but never assembled into anything larger than a few hundred kilometers across. You are moving into that region now. The sun behind you has shrunk to a disk significantly brighter than any star, but no longer warm on your skin the way it is on Earth. At this distance, approximately 2.7 astronomical units, which represents a typical mid-belt position, sunlight takes about 22 minutes to reach you. If the sun were to go dark this instant, you would not know it for more than 20 minutes. The space around you is quiet. Not silent in any absolute sense. Space is never truly silent when you have instruments sensitive enough to detect the particle flux of the solar wind, the faint microwave glow of the cosmic background radiation, the occasional impact of an interplanetary dust particle against any surface you occupy, but quiet in the sense that matters here, vast, slow, and without urgency. You are drifting at a speed consistent with a stable circular orbit at this distance, roughly 20 kilometers per second relative to the sun. That is fast by any human standard. A commercial aircraft travels at about 0.25 kilometers per second. You are moving at 80 times that velocity, but on the scale of the solar system, this motion feels like stillness. The stars do not shift their positions noticeably. The sun creeps only slowly across whatever reference frame you use to track it. The orbital mechanics of this region operate on timescales of years and decades, not minutes and hours. Ahead of you, roughly visible at distance, is an irregular mass of rock. It is classified as an S-type asteroid, silicaceous, meaning its primary composition is silicate minerals mixed with metallite inclusions, the kind of material that makes up the crusts and mantles of terrestrial planets. It is approximately 11 kilometers in its longest dimension and perhaps 6 kilometers across at its widest point. Its surface is covered in a layer of pulverized rock dust called regolith, created by billions of years of micrometeorite bombardment. Every impact, no matter how small, breaks surface material into smaller fragments, and over geological time, those fragments accumulate into a fine gray powder that blankets everything. The asteroid is rotating. You can tell because the shadowed side is slowly rolling into sunlight as you watch, a rotation period of somewhere between 4 and 12 hours, typical for objects of this size. The boundary between the sunlit and shadowed hemispheres, the terminator line, is sharp in the absence of any atmosphere to scatter light. On one side, the rock is illuminated in harsh, flat sunlight with no sky to soften it. On the other, the darkness is absolute. There is no wind here, no erosion in the terrestrial sense. Craters from ancient impacts are preserved with extraordinary precision, unchanged in billions of years except by subsequent collisions. You are looking at a surface that has not been meaningfully altered since before Earth's continents took their current shape, before complex life evolved, before the oceans reached their current chemistry. This rock is older than almost everything you have ever touched. You reach out, not literally, but in the sense of directing your attention, and consider what you are looking at. S-type asteroids like this one are the source material for the most common class of meteorites found on Earth. ordinary chondrites, which contain small spherical structures called chondrules, glass-like beads formed in the early solar nebula when dust and gas were flash-heated to melting temperatures by energetic events we do not yet fully understand. Inside this rock, those chondrules are preserved exactly as they formed more than 4.5 billion years ago, before the Sun was 1% of its current age. You drift past it. The asteroid belt is not one kind of thing. If you were to map the composition of asteroid belt objects as a function of their distance from the Sun, you would find a gradient, a systematic change in chemistry moving outward from the inner belt to the outer. In the inner region, roughly 2.2 to 2.5 astronomical units, S-type asteroids dominate, the silicate-rich, relatively dry bodies that resemble the material of the terrestrial planets. Moving outward through the middle belt and into the outer belt, between 2.5 and 3.2 astronomical units, the dominant population shifts to C-type asteroids, carbonaceous, darker, richer in carbon compounds, hydrated minerals, and organic material. C-type asteroids are among the darkest objects in the solar system. Their albedo, the fraction of incoming sunlight they reflect, can be as low as 3%. Coal reflects more light. When you look at a C-type asteroid in the outer belt, you are looking at a surface that absorbs nearly all the light that falls on it. A darkness so complete, it reads almost as an absence rather than a surface. But the darkness is not emptiness, it is chemistry. The minerals on C-type asteroid surfaces have been altered by liquid water at some point in their history, water that existed inside these bodies when they were young and still generating heat from radioactive decay, water that percolated through their interiors and chemically reacted with silicate minerals to produce clays and hydrated compounds. The water is gone now, locked into crystal structures, or long since lost to space, but the chemical signature it left behind is still there, detectable by spectroscopy, telling the story of a wetter past in the cold outer belt. And then there are the M-type asteroids. Metallic, dense, the exposed interiors of bodies that once grew large enough to differentiate, to separate under their own internal heat into a rocky outer layer and a metal-rich core, just as Earth and Mars and all the terrestrial planets did. Something shattered those differentiated bodies long ago. Catastrophic collisions in the early solar system broke them apart, and what survived were their cores, raw, exposed metal, nickel-iron alloys floating in the blackness between worlds. One of these objects, 16 Psyche, located at roughly 2.9 astronomical units, is thought to be the exposed iron-nickel core of an ancient differentiated protoplanet. Its mass is approximately 1% of the entire asteroid belt. The nickel and iron in its structure, if it were somehow extracted and valued at current commodity prices, would represent a quantity of metal so far beyond any earthly economy that the analogy ceases to have meaning. Psyche is not a target for mining, not yet and perhaps not ever. It is, for now, a scientific object, a place where we can study the interior composition of rocky planets without having to drill thousands of kilometers through their crusts. You leave the metal dark shape of a hypothetical M-type body behind you and continue drifting outward through the middle belt. The sun is a smaller point of light now, noticeably diminished from what it looks like on Earth. It is still the dominant object in the sky by an enormous margin, far brighter than any star, but it no longer fills space with warmth the way it does on Earth's surface. At this distance, the solar flux is approximately 1/5 of what Earth receives. The temperature of a surface in direct sunlight at this location reaches roughly -80 degrees Celsius on the side facing away from the sun and may warm to perhaps -30 degrees Celsius on the sun-facing side. A narrow thermal window, but a window nonetheless. Somewhere in the outer belt, things begin to feel different. The density of detectable objects does not change dramatically, but at a distance of approximately 2.77 astronomical units from the Sun, within what astronomers classify as the outer asteroid belt, there is something that is not like any of the rocks you have passed. It is round. Not approximately round, the way large boulders can appear round when seen from a distance. Genuinely spherically round, a shape that can only occur in a natural body when that body has sufficient mass to generate enough internal gravity to overcome the material strength of rock and pull all its surface material toward its center of mass. This process, called hydrostatic equilibrium, requires a minimum mass that depends on the composition of the object. For rocky bodies, the threshold is roughly a few hundred kilometers in diameter. For icy bodies, the threshold is lower. The object you are approaching has a diameter of 945 kilometers. It is a world. It is the largest object in the asteroid belt, containing approximately 1/3 of the belt's total mass inside its single, round, cratered body. It has a mean density of approximately 2.16 grams per cubic centimeter, lower than most rocky asteroids, which typically range from 2.5 to 3.5 grams per cubic centimeter. That lower density, combined with surface spectroscopy showing water-bearing minerals, suggests that a significant fraction of its interior volume may be water ice. Beneath the rock, there may be an ocean. The surface you are approaching is gray-brown and heavily cratered, pocked with the record of 4 billion years of impacts. The overall shape is not perfectly spherical. The poles are slightly flattened, and there are irregular terrain features, ancient impact basins, scarps, and ridges that speak to a complex geological history. But the dominant impression is roundness, completeness, a sense of closure that the irregular fragments of the belt do not possess. This is Ceres, named by its discoverer's colleagues after the Roman goddess of agriculture and the harvest, the same figure the Greeks called Demeter, mother of Persephone, goddess of grain and seasonal return. The name was chosen because the asteroid belt was thought at the time to lie between the orbits of Mars and Juno, and a goddess of abundance seemed appropriate for a body positioned between the two. The name was given in 1801. Ceres will keep it for as long as the solar system survives. You are close enough now to see surface detail without instruments. The largest crater visible from this approach, an impact basin roughly 280 kilometers wide, named Kirwan after a spirit associated with the growing season, covers a significant portion of the hemisphere facing you. The crater floor is smooth compared to the surrounding terrain, suggesting it was partially resurfaced after the impact, possibly by cryogenic material welling up from below. Not lava, not the molten rock that fills impact basins on the Moon or Mars. Something colder. Something with water in it? The word geologists use is cryovolcanism, the process by which ice, or a mixture of ice and water and dissolved minerals, behaves like magma in a world cold enough that water is the dominant geological fluid. It is still technically active on Ceres, not extinct, not finished. The Dawn spacecraft, as it approached Ceres in the spring of 2015, detected water vapor escaping from the surface, intermittent plumes of sublimating ice liberated into space when the subsurface ice is warmed by sunlight at certain orbital positions. The rate of water loss is small, a few kilograms per second at peak activity. But it is real, and it is ongoing, and it means that this object, this remnant, this leftover, this body that never became a planet, is not geologically dead. It is still doing something. Your approach continues. The sun is now low behind you, casting long shadows across the crater floors and ridgelines ahead. The surface detail is resolving from abstraction into reality. Individual boulders on the crater rims, the subtle color variations that indicate different mineral compositions, the overall texture of a world that has been shaped by cold and time, and the slow work of internal heat. You are descending. Not quickly. There is no atmosphere to create friction, no heat of re-entry, no rushing wind, just a slow convergence with a gray-brown surface that grows larger and more detailed with each passing minute of your approach. The terrain below is ancient. Much of it dates from the late heavy bombardment period, roughly 3.9 billion years ago, when the inner solar system was subjected to an intensified period of large impactor collisions as the giant planets shifted their orbital positions and disturbed the populations of comets and asteroids throughout the system. The large impact basins on Ceres are the scars of that era. They are the same age as the largest craters on the Moon, on Mars, on Mercury. Everything in the inner solar system carries the marks of that time. But Ceres also shows younger features. Fresher craters with sharper rims, surface flows that appear to have happened geologically recently, not in the last few thousand years, but in the last few 100 million, which is young by the standards of a 4-5 billion year old solar system. The evidence suggests that Ceres has not been geologically inert for its entire history. It has experienced episodes of resurfacing, of outgassing, possibly of cryovolcanic activity at irregular intervals, driven by the slow decay of radioactive elements in its rocky core. The heat is still there. Not enough to melt rock, not enough to drive plate tectonics or build volcanic mountains of silicate magma, but enough perhaps to keep some portion of a subsurface water layer in a liquid or semi-liquid state, a brine, a slush, a zone of impure water kept mobile by dissolved salts that lower its freezing point. You are close to the surface now. The horizon of Ceres, seen from low altitude, curves away from you in every direction with a curvature noticeably sharper than Earth's horizon. The escape velocity here is only 0.51 kilometers per second, roughly 1/40th of Earth's, which means the gravity holding you to this world is gentle by any terrestrial standard. You would weigh approximately 3% of your Earth weight on this surface. A single unassisted human step could carry you several meters upward before you drifted back down. The surface beneath you is covered in regolith, pulverized, ancient. The texture of cold gray flour spread across a floor that has not been disturbed in geological time. And ahead of you, still perhaps 50 kilometers away, but growing closer with every moment of your slow descent, there is something that does not belong. 2 points of light. White, brilliant, blazing out of a crater floor surrounded by shadow. They are not a reflection. They are not an artifact of your instruments or your perception. They are real, and they are waiting, and whatever created them is still happening beneath the floor of that crater right now. You let your descent continue. The lights grow brighter as you approach, and the crater walls rise around them like a theater built by an ancient collision, and somewhere beneath the salt crust that is creating that impossible white glow, something that might once have been an ocean is finding its way to the surface of a world that was never supposed to become one. The surface comes up to meet you, quiet and slow, as it has been doing for the last 4.5 billion years. Tonight, you have arrived exactly where you were always going. You hold position. The two bright spots are directly ahead of you now, approximately 30 kilometers distant, centered in the floor of the crater that mission planners named Occator after the Roman deity of harrowing, the agricultural act of breaking up soil after plowing, of preparing the ground, an apt name for a crater whose floor, it turns out, has been broken and reformed by processes that no one anticipated when the first images came back. The crater itself is roughly 92 kilometers in diameter and 4 kilometers deep. It formed approximately 20 million years ago, young by Ceres standards, a recent wound in the ancient surface. The impactor that created it struck hard enough to fracture the crust beneath the crater floor, opening pathways upward from whatever lies below. And what lies below, the data now strongly suggests, is brine. Not pure water, brine, a concentrated saline solution rich in sodium carbonate and ammonium chloride and other dissolved minerals, kept partially liquid by the combination of subsurface heat and its own dissolved salt content, which lowers its freezing point below that of pure water. This brine has been slowly percolating upward through the fractures opened by the Occator impact, reaching the surface, and then evaporating into the near vacuum that passes for Ceres' atmosphere. What is left behind when saline water evaporates into a vacuum is salt. Sodium carbonate, natrite, is one of the brightest naturally occurring minerals in the solar system. Its reflectivity, its albedo, is approximately 50% on a surface where the surrounding terrain reflects only 6 to 9% of incoming sunlight. Patches of sodium carbonate stand out with the visual intensity of floodlights in a dark room. The central bright region in Occator Crater, designated Cerealia facula, facula is the Latin word for torch, has an albedo of approximately 50%, roughly 6 times brighter than the average Ceres surface. The torch metaphor is accurate. From orbit, before the Dawn spacecraft was close enough to resolve surface detail, the two bright spots looked exactly like that. Two torches burning in the darkness of the crater floor. They confused the scientists watching the imagery come in. Hypotheses circulated. Ice exposed by the impact. Cryogenic material, volcanic venting, reflected internal light from some subsurface luminescent process, a theory that was not taken seriously but was briefly considered in the absence of better information. The truth was stranger than most of the hypotheses, and simpler. Salt water evaporating in vacuum, depositing minerals on a crater floor. A process that happens, in a sense, in every terrestrial salt flat when a body of saline water dries out, but happening here in an environment more than 400 million kilometers from Earth, on a world with no weather, no liquid surface water, no atmosphere worth speaking of, and a surface temperature that averages -105 degrees Celsius. You drift closer to the crater rim. Below you, the crater floor is not a uniform surface. The Cerealia facula, the central bright deposit, sits atop a dome-shaped structure roughly 10 kilometers in diameter and roughly 500 meters high, slightly elevated above the surrounding crater floor. This dome is thought to be the direct expression of the upwelling brine beneath it, a mound pushed up by material rising from depth. It is geologically young. Infrared measurements suggest it may have been active within the last few million years, and some models suggest intermittent activity even more recently. To the east of the central dome, a scattering of smaller bright deposits marks the floor of the crater, the secondary faculae, also named after celestial and agricultural deities from various traditions. These satellite deposits are less concentrated, their albedo slightly lower, suggesting they formed at different times or from slightly different brine compositions. Together, the central and peripheral deposits create a pattern that, seen from directly above, looks almost intentional, a central beacon surrounded by smaller lights, like a signal in a dark field. No one put them there, geology did. But for a moment, you understand why the first humans who saw this image needed a few seconds to accept that they were looking at a natural phenomenon. You settle to a slow hover at approximately 2 kilometers above the crater floor. The scale becomes real at this altitude. The bright deposit below you is not a small feature. It covers an area larger than many terrestrial cities. The dome structure at its center rises visibly above the surrounding floor, its surface a blinding white in the low-angle sunlight that reaches down into the crater. The crater walls curve away from you in every direction, rising 3 to 4 kilometers above the floor, creating a bowl of shadow and stone that has been accumulating the slow drip of subsurface brine for 20 million years. The silence here has a quality to it. On Earth, silence is never absolute. There is always air movement, biological activity, the infrastructure noise of civilization. In space, the silence is physically different. There are no molecules around you to carry pressure waves. Sound, in the ordinary sense, does not exist here. Whatever is happening below you, the slow upwelling of brine through fractured rock, the deposition of sodium carbonate crystal by crystal on the growing mound, happens without the smallest vibration reaching your awareness. You are watching geology happen, slowly, in total acoustic silence. It occurs to you, holding position above Occator Crater in the dark of the outer asteroid belt, that the story of Ceres is not a simple story of failure. The word has been used about this world in a loose way since the 19th century. Ceres failed to become a planet. The material of the asteroid belt failed to coalesce. Jupiter interrupted the process before it could complete itself. In that framing, everything in the asteroid belt is a remnant, a leftover, a relic of something that should have been more than it became. But the brine beneath you does not know it is a remnant. The radioactive isotopes decaying in the rocky core of Ceres, uranium-238, thorium-232, potassium-40, do not know the planet they are heating was classified as a dwarf by human astronomers in 2006, the same year that Pluto lost that designation. The sodium carbonate crystallizing on the floor of Occator Crater does not know it is doing so on a body that, according to the International Astronomical Union's formal definition, fails to meet the criterion of having cleared the neighborhood of its orbit. These processes simply continue. The Dawn spacecraft detected, in its high-resolution compositional mapping of Ceres, that the distribution of sodium carbonate is not limited to Occator Crater. Deposits of bright material occur at multiple other locations across the surface, smaller, less concentrated, but chemically consistent. The brine activity, it appears, is not isolated to the Occator fracture system. It may reflect a more broadly distributed subsurface reservoir, a lens or layer of saline liquid that exists at some depth across a significant portion of the world's interior. The concept of a subsurface ocean on Ceres is more speculative than the equivalent concept on Europa or Enceladus, those moons of Jupiter and Saturn, where the evidence for liquid water beneath ice shells is considerably stronger. But Ceres has density and compositional data that are consistent with a substantial water-ice mantle overlying a rocky core, and the brine evidence at Occator suggests that some of that water remains liquid or semi-liquid at depth. The total water content of Ceres, if the current models are correct, may be larger than the total volume of fresh water in all of Earth's lakes, rivers, and groundwater combined. This is not a dry world. It is a cold world, a compressed world, a world that had less energy to work with than the larger bodies of the inner solar system, but it is not empty of water. The material that built Ceres included, from the beginning, significant contributions from the outer solar nebula, where water ice condensed beyond what is called the frost line, the distance from the young sun beyond which temperatures were cold enough for water to exist as a solid rather than a gas. The frost line in the early solar system lay at approximately 2.7 astronomical units. You are currently at approximately 2.77 astronomical units. You are sitting at the historical boundary of the frost line, on one side of this invisible demarcation. In the history of the solar system's formation, rock and metal solidified from the nebula. On the other side, water ice joined the rock and metal as a primary building material. Ceres formed near that boundary, incorporating both dry silicate material and a substantial fraction of ice, creating a body with a composition and an interior structure unlike anything in the inner solar system, and unlike most of the smaller, purely rocky bodies that surround it in the asteroid belt. It is a hybrid world, a transitional world, a threshold. You look out over the crater rim toward the sunlit terrain beyond. The broader surface of Ceres stretches away from you in every direction, gently curved, covered in the muted tones of ancient regolith, punctuated here and there by the slightly brighter rims of younger craters. There are mountains, not high mountains by terrestrial standards, but real topographic relief, ridges and scarps in the raised rims of ancient impact structures. One feature in particular draws attention even at this distance. To the north, visible as a slightly elevated profile against the sky, is a structure that does not fit the expected morphology of an impact world. It is not a crater. It is not a ridge formed by tectonic deformation. It is a mountain, an isolated conical peak rising approximately 4 kilometers above the surrounding terrain, with a base roughly 17 kilometers across at its widest point. It was there before dawn arrived. It is there now. It has a name, Ahuna Mons. And what created it is not an impact. What created it is something that should, by conventional planetary science, only occur on much larger and more energetically active worlds. You begin moving toward it, slowly maintaining your low altitude above the Ceres surface, watching the distant peak grow incrementally larger as you cross the gray-brown terrain between Occator Crater and whatever awaits at the base of that impossible mountain. The sun is low on the horizon from this position. The shadows are long. The bright spots of Occator fade behind you as you move north, reduced to a white gleam at the edge of your peripheral awareness, and the terrain ahead becomes increasingly unfamiliar, older, more eroded in some regions, then suddenly younger and less cratered in patches that suggest localized resurfacing events at irregular points in geological history. Ceres is telling you its history through its surface. You are reading it at low altitude, kilometer by kilometer, and every feature you pass has a story told in impacts and ice, and the slow physics of a world too small to hold its heat for the full span of solar system time, but large enough to hold it for most of it. Large enough to still be warm somewhere beneath your feet. Large enough to still be doing something that no one expected when astronomers first cataloged it as a minor planet, a belt object, a remnant. The mountain ahead is not a remnant. It is new. Geologically, recently, improbably new, and it was built not by the violence of an impact, but by the slow, cold upwelling of material from inside a world that was never supposed to produce such things. You close the distance between yourself and Ahuna Mons, and the shadows lengthen across the ancient floor of the asteroid belt's only dwarf planet, and the question that has been forming since you first saw those two bright spots in the dark crater floor becomes something you cannot look away from. What is still happening inside this world? The answer is somewhere just ahead. The terrain below you changes as you approach. The regolith here, the pulverized surface layer that covers most of Ceres, is thinner in patches, interrupted by outcrops of material that appears slightly different in color and texture from the surrounding plains, slightly brighter, more reflective. The same sodium carbonate signature that blazes so brilliantly in the Occator deposit appears here in much smaller concentrations, scattered across the terrain as faint bright streaks that a camera at orbital altitude would record as minor anomalies, barely statistically distinct from the noise of the surface composition data. But at low altitude, at slow speed, they are visible. They are everywhere. The brine is not limited to Occator. It is distributed across this hemisphere of Ceres in ways that suggest a broad subsurface source rather than an isolated pocket of liquid beneath a single impact structure. The evidence is faint but consistent, and consistency in science carries weight that individual observations do not. You fly above the scattered traces of ancient and recent brine activity, and Ahuna Mons grows ahead of you, and the long Syrian night begins to deepen across the hemisphere behind you as the sun drops lower toward the horizon of this small, stubborn, improbably active world. It has been here for 4.5 billion years. It will still be here long after this night ends. For now, the mountain is close, and the cold and the silence hold you steady, and the place between worlds where something extraordinary refuses to stop happening is exactly where you are. The spacecraft that revealed all of this did not arrive in a hurry. NASA's Dawn mission launched on September 27, 2007, from Cape Canaveral aboard a Delta II rocket. Its destination was not originally Ceres alone. Dawn was designed to orbit two destinations sequentially, the asteroid Vesta and then Ceres, a mission architecture that had never been attempted before with a single spacecraft. Conventional chemical propulsion spacecraft carry a fixed amount of fuel and must commit to a single trajectory. They do not have the energy budget to enter orbit around one body, conduct a full science mission, then depart and travel to a second body and enter orbit there. Dawn could do this because it was not powered by conventional chemical propulsion. Its primary propulsion system used 3 ion engines, devices that ionize xenon gas by stripping electrons from individual atoms and then accelerate the resulting ions through an electric field, expelling them at extremely high velocities to generate thrust. The thrust produced by each ion engine was tiny by rocket standards, approximately 92 millinewtons, roughly equivalent to the weight of a sheet of paper resting on your hand. At that force level, it would take Dawn's ion engines 4 days of continuous firing to accelerate the spacecraft from a standing start to highway speed. But in space, with no atmospheric drag and no requirement to fight gravity once a trajectory is established, constant low thrust applied continuously over months and years accumulates to velocities that chemical rockets cannot match without carrying prohibitive quantities of propellant. Dawn's ion engines fired for more than 70% of the mission's cruise phase, consuming a total of approximately 425 kilograms of xenon propellant over the course of the mission, a tiny mass fraction compared to what a chemical spacecraft would have required for the same mission. Dawn arrived at Vesta in July 2011. It orbited Vesta for 14 months, mapping its surface, measuring its gravity field, and analyzing its composition with a suite of instruments that included a framing camera, a visible and infrared mapping spectrometer, and a gamma ray and neutron detector capable of determining the elemental composition of the top meter of the surface. Vesta turned out to be the source body of a well-studied class of meteorites called HED meteorites, Howardites, Eucrites, and Diogenites, a connection that allowed scientists to directly correlate the meteorite record on Earth with remote sensing data from the asteroid itself. Then Dawn departed Vesta and began the 14-month journey to Ceres. It entered Ceres orbit on March 6, 2015, becoming the first spacecraft ever to orbit a dwarf planet, and the first to orbit 2 extraterrestrial bodies in sequence, as it spiraled gradually inward from its initial capture orbit through a series of progressively lower science orbits. Its cameras began resolving the surface in detail that no telescope had ever achieved. The bright spots were visible in the very first medium-resolution images. Scientists at the Jet Propulsion Laboratory and the Dawn science team spent weeks in public discussion of what they might be, while the spacecraft continued its approach and the images grew steadily sharper. The debate was genuine. The instruments available for analysis, the framing cameras, color filters, the infrared spectrometer, could characterize the composition of the bright material, but only once the spacecraft reached a low enough orbit to make spectroscopic measurements of the relatively small bright patches. The answer, when it came, was sodium carbonate. Not the ice that some had predicted, not sulfur compounds or silica glass, hydrated sodium carbonate, natrite, mixed with ammonium chloride and other evaporite minerals, the specific chemical signature of evaporated brine. The follow-on analysis was more detailed. The concentration of sodium carbonate in the Cerealia facula is extraordinarily high, higher than has been found anywhere else in the solar system outside of laboratory samples. This level of concentration requires large quantities of brine to have evaporated, leaving behind an increasingly concentrated mineral deposit. The process is ongoing. Measurements of the Occator Crater area showed that the bright deposits are younger than the crater floor that surrounds them, and that the central dome structure is younger still, suggesting that brine upwelling has continued intermittently since the Occator impact 20 million years ago, and may be continuing today. Dawn's mission officially ended on November 1st, 2018, when the spacecraft exhausted its remaining hydrazine attitude control propellant and could no longer orient its solar panels toward the sun or its antenna toward Earth. It went silent in Ceres orbit, where it remains today, unable to land due to planetary protection protocols designed to prevent biological contamination of a potentially water-bearing world, unable to depart due to exhausted fuel. Dawn will remain in orbit around Ceres for at least 20 years before orbital decay brings it to the surface. It will be the first human-made object to rest on a dwarf planet. Ahuna Mons rises from the Syrian plain with a geometry that does not belong here. Everything else on this surface, the craters, the ridges, the eroded scarps, the faint depressions left by ancient impacts that were themselves then overlaid by newer impacts, everything else follows the logic of a battered, ancient world shaped primarily by collisions and slow weathering under vacuum. The dominant landform language of Ceres is the circle. Craters nested inside older craters. Rims worn down by micrometeorite gardening over geological time, a surface that records violence in rings. Ahuna Mons is not a ring. It is a dome, a steep-sided, symmetric, solitary upwelling, roughly 17 kilometers across at its base and roughly 4 kilometers tall at its crest, a height that would place it among the major peaks of a continental mountain range on Earth, but here rises from a surface with so little gravity that the comparison almost loses meaning. Its flanks are steep by the standards of Ceres, angles of roughly 40 degrees in places, and its surface is brighter than the surrounding plains, reflecting more sunlight, suggesting that the material composing it is compositionally distinct from the ancient regolith that covers most of this world. The current leading scientific interpretation is cryovolcanism. Not volcanism in the silicate sense, not the eruption of molten rock driven by the radioactive decay heat that powers volcanic systems on Earth, Io, and Mars. Cryovolcanism is the cold equivalent, the eruption or extrusion of material in which water, or a mixture of water and ammonia and salts, plays the role that molten rock plays in conventional volcanism, in an environment cold enough that water ice behaves like bedrock, that is, in most of the outer solar system beyond the frost line. A pocket of liquid water under sufficient pressure can force its way upward through fractures in the overlying ice shell, emerging at the surface and freezing into new terrain. On Enceladus, the icy moon of Saturn, cryovolcanism produces spectacular water vapor geysers from a subsurface ocean that is now well documented. On Titan, Saturn's largest moon, flows of liquid methane carve channels in water ice bedrock the way terrestrial rivers carve channels in granite. On Europa, the deformed and refrozen surface of Jupiter's most geologically complex moon, cryovolcanic and tidal processes have erased almost all impact craters, producing a young surface that records tens of millions of years at most. On Ceres, the evidence is subtler. Ahuna Mons does not erupt. It does not spray material into space. What it appears to have done over an extended geological timescale is ooze upward, a slow extrusion of viscous, water-rich material from a pressurized subsurface source building a dome of frozen brine and hydrated mineral deposits that gradually solidified as it was exposed to the near-vacuum environment of the surface. The age of Ahuna Mons is estimated at somewhere between 200 million and 800 million years, geologically young for Ceres, but old by any human scale. The wide range in the estimate reflects the difficulty of crater counting chronology on a body where the impact flux is not as well constrained as it is for the Moon or Mars. What is clear is that Ahuna Mons did not exist in the early history of Ceres. Something in the interior of this world produced it at a relatively recent geological moment, and it may not be the only cryovolcanic feature. Analysis of the broader Ceres topography by scientists working with dawn data identified a category of features they termed domes, low relief, roughly circular elevated structures distributed across the surface that may represent older, more eroded cryovolcanic constructs. If Ahuna Mons is geologically young and therefore still retains its original steep slopes, then older cryovolcanic domes on Ceres would have been progressively flattened and smoothed by the process of viscous relaxation, the slow plastic flow of ice under its own weight over millions of years, which causes steep features to gradually slump toward lower relief forms. The prediction is testable. If the domes are indeed older cryovolcanic structures, their morphology, their height to diameter ratios, their slope angles, their surface textures should follow predictable curves based on the assumed composition and temperature of the Cerean subsurface. The data so far are consistent with this interpretation. You're standing at the base of Ahuna Mons now. The scale of the feature, seen from ground level rather than from low orbital altitude, is different from what you anticipated. The summit is not dramatically high by terrestrial standards. 4 kilometers is well below the height of many mountain peaks on Earth, but on a world with a surface gravity of only 0.27 meters per second squared, roughly 2.8% of Earth's gravitational acceleration, even a 4-kilometer dome represents a significant concentration of geological energy. The material that built this structure was pushed upward against gravity from some depth below, and on Ceres, where the escape velocity is barely above half a kilometer per second, the physics of building a mountain work differently than they do on Earth. The surface beneath your feet is not the ancient gray regolith of the surrounding plains. It is brighter, slightly blue-tinted in the spectrum of reflected sunlight, which is consistent with the presence of hydrated salts, minerals that contain water molecules locked into their crystal structures, the chemical residue of liquid water that was present when these minerals formed and has since been bound into solid form. The surface is also younger, fresher, less gardened by micrometeorite bombardment than the ancient terrain you crossed to get here. You are standing on something that came from inside this world not very long ago. In geological terms, in terms a geologist would call recent. The view from the base of Ahuna Mons encompasses a significant portion of the northern Cerean hemisphere. The terrain you crossed from Occator Crater stretches away to the south, punctuated by the circular scars of impacts at varying states of erosion. The horizon curves visibly, the sharpness of its curvature a constant reminder that you are on a small world, 945 kilometers in diameter, a body that could fit within the borders of a medium-sized terrestrial country. Beyond the visible horizon in every direction, other features wait that the Dawn spacecraft mapped in the course of its 537-day orbital mission around Ceres. There are the large impact basins, Kirwan, the largest at 280 kilometers in diameter, Yalode, 270 kilometers, Urvara, 170 kilometers. Each named according to the convention adopted by the International Astronomical Union for Ceres, deities and personifications of agriculture and plants from world traditions, continuing the harvest goddess naming logic that goes back to Piazzi's original choice in 1801. There are the chasmata, long, narrow troughs running across the surface, the product of extensional tectonics, of the Syrian crust being pulled apart at some point in its geological history. Rao Chasma, Samhain Chasma, named after the Celtic harvest festival, the origin of the modern Halloween. These features suggest that Ceres has not been a purely passive, impact-shaped body. It has experienced internal stresses that deformed its surface from below. There is Occator Crater, a young impact structure whose rays, the streaks of bright material thrown outward by the impact, are still visible across the surrounding terrain, indicating that the impact happened recently enough that those bright rays have not yet been darkened by space weathering. And there are the bright deposits, the faculae that appear not just in Occator, but at dozens of locations across the surface, in varying concentrations and states of preservation, telling the same story of briny upwelling in different locations and different geological moments across the history of this world. Ceres is not simple. It is layered, literally and in the scientific sense. Beneath the ancient regolith, there is a crust of mixed rock and ice. Beneath the crust, current models suggest a thicker layer of ice-dominated material, an ice mantle, perhaps hundreds of kilometers thick, possibly containing a layer of partially liquid or slushy brine somewhere within it. At the center, a rocky core roughly 360 to 440 kilometers in radius, composed of silicate minerals and metallic components, still generating a small amount of radiogenic heat from the decay of long-lived radioactive isotopes. The radiogenic heat is the key. Uranium-238 has a half-life of approximately 4.47 billion years, nearly as old as the solar system itself. Thorium-232 has a half-life of 14.05 billion years, longer than the current age of the universe. Potassium-40 has a half-life of 1.25 billion years. These isotopes were incorporated into the rocky material of the early solar system in quantities that have been diminishing ever since, but diminishing slowly enough that significant quantities remain active today in the rocky cores of bodies large enough to retain them. In Earth, the heat generated by these isotopes drives plate tectonics, maintains the liquid outer core that generates Earth's magnetic field, and contributes to volcanic activity at hot spots around the planet. In Ceres, the same isotopes generate far less heat. The rocky core is smaller, the total radioactive inventory is smaller, but they generate enough to influence the thermal structure of the interior, to maintain some portion of the ice mantle at temperatures above the melting point of brine, and to drive the slow geological processes that produced Ahuna Mons and the brine deposits of Occator. Ceres is warm inside. Not warm by human standards, not warm in any way that would be detectable without sensitive instruments, but warm in the sense that matters to a planetary scientist, warmer than it would be if it were a purely inert, heat-depleted body. Warm enough to still be doing things. You begin a slow ascent of Ahuna Mons. The low gravity makes the physical mechanics of climbing straightforward. Each step carries you farther than it would on Earth, and the slope, though steep by Cerean standards, requires no extraordinary effort to traverse in this gravitational environment. The surface beneath each step is firm, the hydrated mineral crust more cohesive than the loose powder of the ancient terrain below, offering better purchase. As you climb, the view expands. The curvature of Ceres becomes more pronounced. What was already visible as a sharp horizon at surface level becomes, from even a few hundred meters of altitude on Ahuna Mons, a clearly curved boundary with the blackness of space. The asteroid belt spreads out in your mental map, not visible as discrete objects from this altitude, but present as an understood context, a conceptual field of debris extending hundreds of millions of kilometers in every direction from this point. The sun, seen from the summit of Ahuna Mons, is a brilliant point of light, roughly 1/3 the angular diameter it presents when seen from Earth. It illuminates the Cerean surface with the flat, unfiltered intensity of space. No atmospheric scattering to soften it, no sky to spread it into a diffuse warmth. Shadows are black and absolute. Illuminated surfaces are sharp and bright. You reach the summit. The terrain here is almost flat, a broad, slightly irregular top surface, several kilometers across. Not a sharp peak, but a rounded plateau. The brightening of the surface material is most pronounced here, the hydrated salt deposits most concentrated, as if the upwelling that built this structure was strongest at the summit, the point of least resistance for the brine, forcing its way up from below. You stand at 4 kilometers above the surrounding plains of Ceres. You are standing on the youngest significant landform, on the largest object in the asteroid belt. And the view from here encompasses a world that spent 4.5 billion years being categorized as a failure, a planet that never formed, a remnant of interrupted processes, a belt object, while quietly beneath its ancient cratered surface, continuing to build new things. The mountain you are standing on did not exist when the dinosaurs were alive. It rose from the ice while mammals were already diversifying on Earth, while the first grasses were spreading across the continents, while the world that would eventually produce the person lying in the dark, listening to this, was slowly becoming the world it is now. Ceres was building a mountain. It did not announce this. It did not need to. The physics of a slowly pressurizing subsurface brine reservoir do not require witnesses. The process happened at whatever rate the internal conditions demanded, indifferent to the biological complexity evolving on the third planet of this solar system, indifferent to everything except the slow arithmetic of pressure and temperature and the viscosity of cold, salt-laden water moving through fractured ice. You sit at the summit of Ahuna Mons and look out across the Cerean surface. The shadows are long now. The sun has moved through its apparent position as Ceres rotates beneath your feet, a rotation period of 9 hours and 4 minutes, faster than Earth's 24-hour day. You have been on this surface for what would be, by Cerean timekeeping, a significant fraction of a full day. The terminator line, the boundary between the lit hemisphere and the dark hemisphere, is moving visibly slowly, crossing the terrain at a rate you can almost track if you watch long enough. Night will come to this hemisphere within a few Cerean hours. And somewhere below you, beneath the bright mineral crust of Ahuna Mons and the ancient gray floor that stretches away from its base in every direction, the brine reservoir that built this mountain is still there, still warm, still pressurized, still doing, at the time scale of geological processes, what it has been doing for hundreds of millions of years. You are sitting on top of evidence that this world is not finished. And in the dark, in the slow warmth of the bed where you are lying, that fact carries a weight that has nothing to do with the low gravity of a dwarf planet, and everything to do with what it means to be in the presence of something that refuses to stop. The asteroid belt stretches out around Ceres in every direction, silent and ancient and full of fragments. And in the middle of all those fragments, one thing is still growing. You take that thought with you as you begin your descent, heading back down through the young bright terrain of Ahuna Mons toward the older surface below, and already your attention is beginning to shift, not away from Ceres, but through it, toward a question larger than this single world. What are all these fragments made of? Not in the mineral sense, not in the compositional sense that Dawn's instruments answered so precisely. In the older sense, in the sense of origins. These fragments are not simply the debris of a failed planet. They are the archive of what the solar system was composed of before any planet had assembled, the raw material preserved in its original state. The most primitive objects in the belt, the ones that escaped not just planetary accretion, but even the internal heating and differentiation that altered the chemistry of larger bodies, carry within them material that has not been meaningfully changed since the first solid particles condensed from the solar nebula more than 4.5 billion years ago. That material includes organic compounds. That material includes amino acids. That material includes the molecular precursors of the chemistry that, on at least one world in this solar system, eventually became alive. You step off the slope of Ahuna Mons onto the ancient plain. The question is already there, waiting in the regolith. It has been waiting for 4.5 billion years. And the answer, when it came, did not arrive from a laboratory or a theoretical model. It arrived in pieces, literally. In fragments of asteroid material that fell through Earth's atmosphere as meteorites, and were recovered, and were analyzed, and were found to contain something that changed the way scientists thought about the origin of life on this planet. The story begins not here on Ceres, but in a field in Victoria, Australia, on a September morning in 1969. A fireball? A sound like a detonation rolling across the pastoral landscape of the Loddon Valley. Then silence. Then, over the following days and weeks, the recovery of approximately 100 kilograms of dark, fragile, crumbly rock scattered across a strewn field, roughly 13 kilometers long and 3 kilometers wide, centered on a small town called Murchison. The Murchison meteorite is one of the most scientifically significant rocks ever recovered on Earth. It is a carbonaceous chondrite, a C-type asteroid fragment, the same compositional class as the dark outer belt asteroids you passed on your way into the belt. Its chemistry had not been significantly altered since its parent body formed in the early solar system. It was a sample of the raw material of planetary formation, delivered by the accident of orbital mechanics to a location where human scientists could pick it up and analyze it. What they found inside changed the questions. More than 90 amino acids have been identified in the Murchison meteorite. On Earth, living organisms use 20 amino acids to build proteins. Of those 20, the Murchison contains at least 14, not in concentrations associated with terrestrial biological contamination, but in distributions and isotopic ratios consistent with extraterrestrial origin, formed by non-biological chemical processes in the early solar system. The meteorite also contains nucleobases, the molecular components of DNA and RNA. It contains sugar molecules, including ribose, the sugar that forms the backbone of RNA. It contains hydroxy acids, fatty acids, and a range of other organic compounds that read, in the context of astrobiology, like a partial inventory of the molecules needed to build a living cell. No one is claiming that life was in the Murchison meteorite. What the data show is something more subtle and in some ways more profound, that the chemistry of life, the specific molecular toolkit that Earth biology uses, is not unique to Earth. It assembles spontaneously, in space, in the absence of life, driven by the same photochemistry and radiation chemistry that operates throughout the solar nebula. The building blocks were available before Earth existed. They arrived here as the planet was forming, delivered by the same bombardment that shaped the early surface. Life did not invent its own chemistry, it inherited it. You are moving across the outer asteroid belt now, away from Ceres, heading through the C-type population, the dark carbon-rich water-altered bodies that represent the most chemically primitive material in the inner solar system. You're surrounded by the source population of the Murchison meteorite and hundreds of others like it. The surface of every C-type asteroid you pass contains hydrated silicates, clay minerals formed by the reaction of liquid water with silicate rock inside the asteroid body during the first tens of millions of years after formation, when short-lived radioactive isotopes like aluminum-26 were still generating heat and melting the ice mixed in with the rock. That liquid water percolating through the interior of the early asteroid dissolved organic molecules and amino acid precursors from the surrounding material, concentrated them, brought them into contact with mineral surfaces that may have served as catalysts for further chemical reactions. The asteroid was, in a limited and non-biological sense, processing chemistry. Not intentionally, not with any mechanism analogous to metabolism, but the physical conditions inside a water-altered carbonaceous asteroid, liquid water, mineral surfaces, organic molecules, gentle warmth from radioactive decay, are conditions that chemists recognize as favorable for the kinds of reactions that produce molecular complexity. The early solar system was full of these reactors. Billions of C-type asteroid bodies, ranging from meters to hundreds of kilometers in size, each one a small chemical processing environment, each one potentially accumulating and transforming organic material for the first 100 million years of solar system history before the water froze again and the radioactive heat sources decayed below the threshold needed to maintain liquid environments. Then the late heavy bombardment began. Approximately 3.9 billion years ago, something, possibly a gravitational resonance event triggered by the migration of Jupiter and Saturn to their current orbital positions, an event now modeled under the name the Nice model after the French city where it was first developed. Something destabilized a large population of outer solar system bodies and sent them raining inward across the inner solar system. The moon's surface was saturated with new craters during this period. Mars was struck by impactors large enough to create basin-scale features. Earth received its share of impacts, and with those impacts came mass. Mass including water. Mass including organic compounds? The current scientific understanding of Earth's water budget suggests that a significant fraction of Earth's oceans may have been delivered by the bombardment of water-rich asteroids and comets during this period and the earlier epoch of heavy bombardment that preceded it. The hydrogen isotope ratios in Earth's water, specifically the ratio of deuterium to ordinary hydrogen, have a value consistent with asteroid delivery, though the precise fraction remains debated. Cometary water has a deuterium ratio that is on average somewhat higher than Earth's ocean water. Asteroid water from C-type bodies matches more closely. The water you are flying through, the ice locked into the structure of the C-type asteroids around you, the brine seeping through the fractures of Ceres behind you, is chemically related to the water in Earth's oceans. It came from the same source material. It was processed in the same environments. And with it, embedded in the meteoritic material that bombarded the early Earth over hundreds of millions of years, came the organic compounds that seeded the planet's surface with the molecular raw materials for the origin of life. This is not settled science. The origin of life remains one of the most genuinely open questions in all of biology and planetary science. The delivery hypothesis, the idea that life's precursor molecules arrived on Earth via asteroid and comet bombardment, is a leading but not exclusive explanation. Molecules identical to those in the Murchison meteorite can also be synthesized on Earth by non-biological processes, given appropriate conditions. The debate is about relative contributions, not about whether extraterrestrial delivery happened at all. It clearly did. The question is how much it mattered. But the question itself has changed. Before the Murchison analysis, before the identification of amino acids and nucleobases in meteoritic material, the origin of life was often framed as a problem of improbable molecular assembly. How, in the chaos of the early Earth, did the right molecules happen to come together in the right conditions to produce the first self-replicating chemistry? After Murchison, the question shifted. The right molecules were already there. They arrived in vast quantities, delivered by the same bombardment that was simultaneously shaping the planet's surface and building up the oceans. The improbable assembly problem became, if not solved, significantly less improbable, because the raw materials were not being generated from scratch on a single planet, but were being manufactured throughout the solar nebula and delivered at scale. You are holding a piece of carbonaceous chondrite in your awareness, not physically, but in the way you hold an idea when it has become real enough to have texture. The rock is dark, almost black, faintly warm from a proximity to a body that still has trace amounts of the radioactive elements that heated its interior 4 billion years ago. Its surface is dull and unremarkable. There is nothing in its appearance that announces what it contains. But somewhere inside the mineral matrix of this fragment, between the chondrules and the clay minerals and the tiny inclusions of presolar grains that formed around other stars before this solar system existed, there are organic molecules that are also present in every cell of every living thing on Earth. The same carbon chains, the same amino group and carboxyl group arrangement that defines an amino acid, the same nucleobase ring structures that encode genetic information in DNA. Not identical molecules, not life, not even close to life, but the same chemistry. You hold the dark rock in your attention and consider what that means for the question of life elsewhere in the universe. If the molecular building blocks of life assemble spontaneously throughout the solar nebula, if they are a natural product of the same photochemistry and radiation chemistry that operates in any molecular cloud collapsing toward a new star, then they are not rare. They are, by the standards of cosmic chemistry, common. Every planetary system forming around every star in the galaxy is presumably building its own population of carbonaceous asteroids. Every one of those asteroids is presumably running the same chemical reactions in its water-altered interior. Every one of those systems is presumably seeding its inner planets with the same organic inventory that was seeded onto the early Earth. Whether any of those planets developed life from those ingredients is a separate question, one that depends on planetary conditions, on the availability of liquid water, on energy sources, on the stability of the environment over the geological timescales that seem to have been necessary on Earth. But the ingredients were there. The ingredients are there. The asteroids around you are not silent remnants of a failed planet. They are the distributed library of the solar system's original chemistry, preserved in cold and darkness, carrying their molecular cargo through the same orbits they have occupied for billions of years, waiting for the conditions that will allow that chemistry to mean something. On Earth, those conditions existed. The delivery happened. The chemistry found its environment. What followed, over the next 4 billion years, eventually produced a species that built instruments sensitive enough to detect amino acids in a piece of rock recovered from a field in Victoria, Australia, and to understand what those molecules meant. The rock fell on September 28, 1969, 56 days before Apollo 12 landed on the moon, at a moment when human beings were, for the first time in the history of life on this planet, beginning to genuinely reach into the space from which that rock had come. The science that Murchison initiated did not stop with that single meteorite. In December 2014, JAXA, the Japan Aerospace Exploration Agency, launched the Hayabusa 2 spacecraft on a mission to a small C-type near-Earth asteroid designated 162173 Ryugu. The name Ryugu comes from Japanese mythology. It is the underwater dragon palace from which the folk hero Urashima Taro returns, carrying a box that ages him instantly when opened. The mythological resonance is apt for an object that carries, sealed inside its ancient mineral structure, chemistry from the earliest moments of the solar system. Ryugu is a rubble pile asteroid, not a single solid body but an aggregate of loosely consolidated rock and dust, held together by its own low gravity, rather than by any intrinsic material strength. Its shape is roughly spheroidal, about 900 meters in diameter, with an equatorial ridge that gives it a silhouette resembling a spinning top when seen from certain angles. Its surface is very dark, an albedo of approximately 4%, consistent with a carbon-rich surface that has been darkened by billions of years of exposure to solar radiation and cosmic ray bombardment. Hayabusa 2 arrived at Ryugu in June 2018 and spent 18 months conducting an extraordinarily detailed investigation of the asteroid's surface and interior. The spacecraft deployed 4 small landers and rovers onto the surface, performed 2 touchdowns to collect surface material, and, in the mission's most technically dramatic moment, fired a 2-kilogram copper impactor into the surface at approximately 2 kilometers per second, creating an artificial crater and then collecting the subsurface material that had been excavated by the impact. subsurface material that had been shielded from space weathering for the entire history of the asteroid. The sample capsule from Hayabusa 2 returned to Earth on December 6, 2020, landing in the Woomera Desert in South Australia, not far in continental terms from the Murchison-strewn field. Scientists recovered 5.4 grams of material from Ryugu, including both surface samples and the precious subsurface material from the artificial crater. The analysis of the Ryugu samples confirmed and extended what the Murchison meteorite had first suggested. The samples contained more than 20 amino acids, including all 5 nucleobases that encode genetic information in DNA and RNA: adenine, guanine, cytosine, thymine, and uracil. They contain uracil, the RNA-specific base, in particularly notable quantities. The isotopic ratios of the organic compounds were consistent with formation in the cold outer solar nebula, beyond the solar system's snowline, in an environment very different from the warm inner solar system, where Ryugu now orbits. The samples also contained liquid water inclusions, microscopic pockets of water trapped inside mineral grains, sealed when the grain formed in the presence of liquid water inside the early Ryugu parent body. These inclusions are not just evidence that water was present, they are samples of that ancient water preserved in their original mineral hosts for more than 4.5 billion years, recovered by a spacecraft and returned to a laboratory on Earth. We have tasted the water of the early solar system. It is salty, alkaline, rich in organic carbon, and it is chemically related to the water in the world's oceans. The C-type asteroids drifting around you are the same population that produced the Ryugu parent body, the Murchison parent body, and hundreds of other meteorites that have fallen on Earth carrying that same ancient chemistry. Each one is a sealed archive. Each one has been moving through this region of the solar system, unchanged in its essential molecular inventory, since before Earth had continents. The asteroid belt recedes slowly behind you as your attention drifts, not away from the science, into it, into the question of what it means that the building blocks of your own biochemistry were forged in molecular clouds before the sun existed, distributed by the collapse of those clouds into protoplanetary disks, processed by liquid water inside small rocky bodies in the early solar system, and delivered to the surface of an infant planet that would spend the next 4 billion years figuring out what to do with them. You are made of asteroid material. Not metaphorically, literally. The carbon in your cells, the nitrogen in your amino acids, the oxygen in your water, these atoms were present in the solar nebula before Earth formed. Some fraction of the organic molecules in your body trace their chemical ancestry through the same processes that produce the organic compounds in the Murchison meteorite. The chain is long and complicated and interrupted by billions of years of biological transformation, but the chain is there. The asteroid belt is not the space between worlds. It is the space between what the universe was and what it became. And you are what it became. The dark rocks drift in their ancient orbits around you, silent and slow, and carrying more history than any library ever built. And the cold of the outer belt settles into the edges of your awareness as the story moves toward its conclusion, and somewhere far behind you, Ceres turns slowly in the dark, its brine still percolating, its mountains still standing, its bright spots still blazing out of the floor of Occator Crater like a signal from a body that had no business being this geologically alive. The sun is small from here, but it is still there. And the question of what else is out there in the billions of other planetary systems circling the billions of other stars in this galaxy is not smaller for the distance. It is larger. It keeps getting larger. And somehow, impossibly, that thought is not frightening. It is the most peaceful thought in the universe. The asteroid belt is not static. Nothing in the solar system is truly static. Every orbit is subject to perturbation. Every trajectory is the product of accumulated gravitational influences, acting over timescales that dwarf any human frame of reference. But the asteroid belt, more than most regions of the solar system, is a place of slow, continuous change. The objects within it are not frozen in the positions they occupied when the solar system formed. They are drifting, gradually, in response to forces so subtle that detecting them required more than a century of careful astrometric measurement and theoretical refinement. The most important of these forces has a name that sounds like the title of an obscure academic paper: the Yarkovsky effect. Ivan Yarkovsky was a Russian civil engineer who worked in the late 19th and early 20th century on engineering problems that had nothing to do with orbital mechanics. In his spare time, he developed a pamphlet, not a peer-reviewed paper, a pamphlet, in which he described a mechanism by which the thermal properties of a small rotating body in space could, over time, cause its orbit to drift. The pamphlet was largely forgotten. Yarkovsky died in 1902. His idea lay dormant for decades until it was independently rediscovered and formalized by scientists working on the orbital dynamics of small solar system bodies in the 20th century. The mechanism is this: a rocky body in space absorbs sunlight on its illuminated hemisphere and re-radiates that energy as thermal infrared radiation. The re-radiation does not happen instantaneously. There is a thermal lag, a delay between when a surface is heated by sunlight and when it reaches its maximum temperature and emits the most radiation. Because the asteroid is rotating, the surface that was heated on the sunlit side has rotated slightly away from the sun by the time it re-radiates. The thermal emission therefore occurs at a slightly different direction than the original absorption. Radiation carries momentum. The asymmetry between absorbed sunlight and re-radiated thermal emission creates a net force, tiny but non-zero. For a 1-meter asteroid, the Yarkovsky force produces an orbital drift of a few centimeters per year. For a 10-kilometer asteroid, the drift is smaller in absolute terms relative to orbital size, but it accumulates over millions of years into a displacement of thousands of kilometers. Over the lifetime of the solar system, the Yarkovsky effect has moved asteroids across the entire width of the asteroid belt. It is responsible for the delivery of asteroids to the Kirkwood Gap resonances, the orbital zones where Jupiter's gravity amplifies eccentricity and eventually ejects objects from the belt. An asteroid that forms far from a Kirkwood Gap may, over hundreds of millions of years, drift close enough to be captured by the resonance and launched toward the inner solar system. This is the mechanism by which the Earth-crossing asteroid population is continuously replenished. This is why meteorites continue to fall on Earth billions of years after the end of the late heavy bombardment. The asteroid belt is leaking, slowly, into the inner solar system. and the inner solar system is occasionally reminded of this fact in ways that are difficult to ignore. The near-Earth asteroid population, objects whose orbits bring them within 1.3 astronomical units of the Sun, currently numbers more than 36,000 cataloged objects above 140 meters in diameter, with the actual population estimated to be considerably larger once objects too small to detect are included. Of these, several thousand are classified as potentially hazardous asteroids, objects whose orbits bring them within 0.05 astronomical units of Earth's orbit, and which are large enough to cause regional to global damage if they were to impact the planet. The probability of any specific potentially hazardous asteroid actually striking Earth within the next century is, for most cataloged objects, very small. Orbital mechanics can be calculated with extraordinary precision for objects whose positions have been measured over many observational arcs. For the current best monitored objects, the probability of Earth impact within the next 100 years can be bounded to less than 1 in a million per year. The risk is real but small, and it is shrinking as the survey programs that catalog these objects continue to expand. But the risk is not zero. And for the first time in the history of this planet, a species with sufficient understanding of orbital mechanics exists to do something about it. On September 26, 2022, a spacecraft named DART, the Double Asteroid Redirection Test, collided with a small asteroid moonlet named Dimorphos, which orbits the larger asteroid Didymos at a distance of approximately 1.2 kilometers. DART was not a large spacecraft. It massed approximately 570 kilograms at impact, roughly the weight of a compact car. It struck Dimorphos at approximately 6.1 kilometers per second. The impact changed the orbital period of Dimorphos around Didymos. Before impact, Dimorphos completed one orbit of Didymos in 11 hours and 55 minutes. After impact, the orbital period was 11 hours and 23 minutes, a change of 32 minutes, roughly 4.5%. The target for mission success had been a change of 73 seconds. DART exceeded that target by a factor of more than 25. For the first time in the 5 billion year history of this solar system, a species from the third planet changed the orbit of another world. The method worked better than expected because the impact did not simply push Dimorphos like a billiard ball. It excavated a crater, ejecting a plume of material estimated at somewhere between 0.3 and 0.5% of Dimorphos's total mass into space. That ejecta carried momentum outward as it departed, and the reaction to that momentum push was additional deceleration of Dimorphos in its orbit. The asteroid's own loosely consolidated structure amplified the effect of the impact by factors that the mission planners had modeled but could not fully predict in advance. The European Space Agency's Hera mission, launched in October 2024, is en route to the Didymos system to conduct a detailed post-impact survey of Dimorphos, measuring the crater, characterizing the asteroid's internal structure, and refining the models of how kinetic impactors interact with different types of asteroid material. The data from Hera will allow scientists to design future planetary defense missions with greater confidence. The asteroid belt gave us the tools for its own monitoring. In a way, the meteorites that fell through Earth's atmosphere over centuries and that were collected and analyzed and found to contain the compositional records of asteroid types provided the baseline understanding of asteroid material properties that informed the DART mission design. The Hayabusa and Hayabusa 2 missions contributed direct measurements of rubble pile asteroid structure. The laboratory analysis of returned samples provided density and porosity data that became inputs in the impact modeling. The study of the asteroid belt is not purely academic. It is, in the most direct sense, planetary self-defense, the application of scientific knowledge about the solar system to the problem of ensuring that the species which developed that knowledge continues to exist long enough to use it. Before the missions, there was only the light. For the first 2 centuries after Ceres was discovered, everything known about the asteroid belt came from telescopes, from the slow accumulation of brightness measurements, spectral analyses, and orbital calculations performed by astronomers who would never come within hundreds of millions of kilometers of the objects they were studying. The tools were ingenious. The data was real, but it was all remote, inferred, not touched. The spectral classifications that divide asteroids into C-type and S-type and M-type were developed from the way these objects reflect sunlight at different wavelengths. Different minerals absorb different wavelengths of light and reflect others, creating spectral signatures that can be compared to laboratory measurements of known mineral samples. By matching an asteroid's reflectance spectrum to laboratory analogs, planetary scientists could determine from Earth what the surface of an asteroid hundreds of millions of kilometers away was probably made of, without ever sending a spacecraft. This technique, called reflectance spectroscopy, gave us the compositional map of the asteroid belt that showed the gradient from dry S-types in the inner belt to water-altered C-types in the outer belt. It gave us the identification of Vesta as the parent body of the HED meteorites, 15 years before Dawn confirmed it in person. It gave us the first hints that the bright deposits on Ceres might be composed of minerals associated with brine evaporation, years before Dawn's instruments confirmed the sodium carbonate identification. Telescopes are still doing this work today. The ongoing surveys, Pan-STARRS, the Catalina Sky Survey, the forthcoming Vera Rubin Observatory, with its legacy survey of space and time, are continuously expanding the catalog of known asteroid belt objects, improving orbital determinations, and adding spectral classifications. When Vera Rubin begins full operations, it is expected to discover more than 5 million previously uncatalogued solar system objects in its first decade of operation, the majority of them in the asteroid belt. 5 million new data points, 5 million new pieces of the puzzle of what the early solar system was made of and how it distributed that material across the orbits where planets were trying to form. The data will take decades to fully analyze. The scientists who will complete that analysis have not yet started their careers. You are moving now through the outer reaches of the asteroid belt, heading toward the boundary where the belt's influence fades into the Jovian region. The objects around you are thinning, not dramatically. The belt does not end at a sharp boundary, but the number density of detectable asteroids decreases as you approach the outer edge, partly because Jupiter's gravity has cleared the outermost resonance zones, and partly because the objects in the outer belt have had longer timescales to be perturbed into Jupiter-crossing orbits, and either ejected from the solar system or captured as Jupiter Trojans. The Sun is noticeably smaller now. Its disk has shrunk to a point where the difference from Earth's sky is obvious, not just measurable. The light it provides is still adequate for your instruments and your perception, but the warmth it carries is less. Surface temperatures in this region of the outer belt fall toward -100 degrees Celsius, even in direct sunlight. This is the cold part of the solar system. The part where things are preserved. An asteroid in the outer belt that has not experienced a major collision in the last billion years will look at its surface almost exactly as it looked a billion years ago. The thermal cycling between sunlit and shadowed hemispheres is too gentle to fracture rock the way freeze-thaw cycles fracture terrestrial geology. The micrometeorite bombardment is slow. The flux of impactors decreases with distance from the sun, following the same gradient as the solar wind. The changes accumulate, but they accumulate slowly. Some of the objects out here are as close to pristine early solar system material as anything in the inner solar system can be. And the question of where to go next, where to send the next spacecraft, the next sample return mission, the next long-duration orbital observatory, is a question that planetary scientists debate with the specific urgency of people who know that each mission takes a decade to develop, that funding is limited, and that there are more scientifically compelling targets in the solar system than the political and budgetary structures of any civilization can address simultaneously. The asteroid belt has not exhausted its scientific inventory. Not even close. 16 Psyche waits for the spacecraft currently traveling toward it. A world of metal, the exposed core of a shattered protoplanet, a place where the interior composition of rocky planets can be studied from the outside without drilling. Earth has an iron-nickel core, similar in composition to what Psyche is thought to represent, but Earth's core lies 6,371 kilometers beneath your feet, inaccessible to any drilling technology that exists or is foreseeable. Psyche offers the possibility of reading that core composition directly from orbit, using instruments that measure gravitational fields and surface elemental abundances from a spacecraft a few hundred kilometers overhead. NASA's Psyche spacecraft, launched in October 2023 aboard a SpaceX Falcon Heavy, is currently traveling toward the asteroid on a trajectory that will bring it into orbit in August 2029. It carries a multispectral imager, a magnetometer to detect remnant magnetic fields from a possible ancient dynamo in the asteroid's metallic interior, a gamma-ray and neutron spectrometer to characterize surface elemental composition, and a radioscience experiment to measure the gravity field and constrain the interior density distribution. If Psyche is what the models suggest, a metallic core fragment, then the magnetometer data will be particularly revealing. If the asteroid was once part of a differentiated body, large enough to generate a planetary dynamo, remnant magnetic signatures may be preserved in its metallic material, recording the strength and direction of a magnetic field that existed more than 4.5 billion years ago, before the collision that shattered the parent body and left Psyche orbiting alone. We may be able to read the magnetic history of a planet that no longer exists. Ceres waits for a follow-on mission that could drill into its subsurface, sample its brine directly, and test the hypothesis of a contemporary liquid layer beneath the ice mantle. A lander on the floor of Occator Crater, equipped with a drill, a mass spectrometer, and instruments to measure heat flow from the interior, could resolve, within a single mission, the question of whether Ceres harbors a contemporary liquid water environment. That question has direct implications for the habitability of small icy bodies throughout the outer solar system, for the interpretation of data from Europa and Enceladus, and for the broader assessment of where in the solar system conditions for life might exist today. These missions will take time. They will take the kind of time that requires accepting that the work being done now is not for the scientists who begin it, but for the scientists who will be young when the data comes back. The Hayabusa 2 team that launched the spacecraft in 2014 was working for a community that would not receive the samples until 2020. The Dawn team that began mission planning in the late 1990s was working for scientists who would still be students when the spacecraft reached Ceres. The DART team spent years preparing for an impact that lasted less than a second. The asteroid belt operates on timescales that make human attention spans seem like a rounding error. And yet, the attention is there. The instruments are there. The quiet accumulation of data, spectrum by spectrum, orbit by orbit, sample gram by sample gram, is building a picture of the solar system's history and composition that no single decade of work could produce, but that decades of patient work are slowly assembling. You are drifting outward now toward the very edge of the belt, where the last cataloged asteroids give way to the vast, relatively empty space between the asteroid belt and Jupiter. The objects around you are fewer, their surfaces older looking, their orbits more stable because they sit in the quiet zones between resonances, far from Jupiter's most energetic gravitational reach. The silence out here has a depth to it. Not the silence of emptiness. The belt is never truly empty, and even at its outer edge there are objects too small to catalog. Dust particles drifting on the pressure of sunlight, the constant low flux of cosmic rays arriving from all directions, but a silence of scale. The nearest star beyond the sun is more than 4 light-years away. The nearest galaxy beyond the Milky Way is more than 2 million light-years away. The universe is almost unimaginably large, and you are in an almost unimaginably small region of it, drifting between 2 of the solar system's inner worlds in a belt of ancient rock that formed before the continents of Earth existed. The distances involved in this evening's journey are worth sitting with for a moment. The inner edge of the asteroid belt, where you entered, lies at approximately 2.2 astronomical units from the Sun. 1 astronomical unit is the mean Earth-Sun distance, approximately 149.6 million kilometers. The inner edge of the belt is therefore approximately 329 million kilometers from the Sun. The outer edge, where you now drift, is approximately 479 million kilometers from the Sun. The width of the asteroid belt, measured radially, is approximately 150 million kilometers. You have traveled, in the course of this night, across a distance comparable to the distance between Earth and the Sun. And you have not left the solar system. You have not even reached the most distant of the 4 gas giants. Neptune, the outermost major planet, orbits at approximately 30 astronomical units, nearly 10 times farther from the Sun than the outer edge of the asteroid belt. The heliopause, where the solar wind meets the interstellar medium and the Sun's direct influence ends, lies at roughly 120 astronomical units. The Oort cloud, the distant reservoir of comets that surrounds the solar system in a vast spherical shell, extends outward to perhaps 100,000 astronomical units. The asteroid belt is close. By the standards of what is out there, you are still practically home. And yet it took a spacecraft with a revolutionary propulsion system more than 7 years to travel from Earth to Ceres. The distances that feel abstract when described in astronomical units are, when translated into mission timelines and fuel requirements, among the most formidable engineering challenges our civilization has yet confronted. The night is deepening around you. Not in any literal sense. There is no sky out here that darkens with the rotation of a planet, no sunset to mark the passage from day to night. But there is a quality to the outer belt, in the cold, in the distance, and the silence, that resembles the texture of late night, the hours when the world's activity has quieted and the mind stops performing its daytime functions and begins simply receiving what is there. What is there in every direction is time. More time than the human mind was built to comprehend. The asteroid belt formed 4.567 billion years ago, when the solar system's age was measured in millions of years rather than billions. The oldest material in the belt, the calcium-aluminum-rich inclusions found in certain carbonaceous chondrites, formed within the first million years of solar system history, before the planets had assembled, before Earth had a surface, before any of the events that would eventually lead to the existence of a species capable of holding this thought. Those grains of ancient mineral are still out here. Inside these dark, drifting asteroids, locked into the mineral matrices of chondrites that have never been significantly heated or chemically altered, there are microscopic grains of material that formed around other stars before this solar system existed. Pre-solar grains, silicon carbide, graphite, corundum, each one an isotopic fossil of a stellar nucleosynthesis event that happened billions of years before the sun was born. They survived the collapse of the molecular cloud that formed this solar system. They were incorporated into the solid particles that became the first asteroids. They have been drifting in these orbits ever since. They predate the sun. You are surrounded by material older than the star at the center of this solar system. Take a moment with that. The star that provides the light by which you see, the energy that maintains the temperature differential between this world's sunlit and shadowed hemispheres, the gravitational anchor that holds the entire architecture of the solar system in place. That star is younger than some of the material in the rocks around you. The sun has been burning hydrogen in its core for approximately 4.6 billion years. The presolar grains in some of these asteroids formed up to 7 billion years ago, around stars that have since exhausted their fuel, collapsed, and possibly exploded. The carbon in those silicon carbide grains was forged in the nuclear burning shells of asymptotic giant branch stars, the late evolutionary stage of sun-like stars. When they expand and cool and eject their outer layers into the interstellar medium in slow stellar winds that carry freshly synthesized heavy elements into the galaxy. The material came from dying stars. It survived the birth of a new one. It has been here ever since, unchanged, waiting, not waiting in any intentional sense, but present, with a patience that has no equivalent in any human experience. You are drifting now in the cold of the outer belt, and the patience of the material around you is entering your awareness in the way that very large things enter awareness, not as a thought that can be held and examined, but as a quality of the space you occupy, a weight that settles without pressing. The orbits of the asteroids around you are stable. Their periods range from roughly 3 to 6 years at the outer edge of the belt. They have been completing these same orbits, give or take the slow drift of the Yarkovsky effect and occasional perturbations from planetary close approaches, for billions of years. Each object has gone around the sun hundreds of millions of times. The orbital paths are worn, in the sense that a path worn into grass by repeated passage is worn, not physically because space does not record passage the way soil does, but statistically, probabilistically, in the distribution of object positions that reflects where they have been spending their time. These objects know their orbits the way a river knows its channel. Not with knowledge, with the accumulated fact of having been there so many times for so long. The cold deepens toward you now. Not aggressively. There is no cold front in space, no wind to carry the chill from shadow to sunlit surface. It is simply the absence of warmth, the fundamental temperature of this region, set by the balance between the solar flux at this distance and the thermal radiation that any surface emits in response. That balance settles to approximately -100 degrees Celsius in the outer belt, and that temperature is the baseline of the environment in which all these objects have been existing, in all their orbits, through all the years. It is a cold that does not demand anything. It simply is. And somewhere in that cold, Ceres is still turning. At this distance, roughly 150 million kilometers behind you, deeper in the belt, Ceres is a pinprick of reflected light, distinguishable from its neighbors only by its brightness and its round shape in high-resolution imaging. The bright spots of Occator Crater are far too small to see from here without instruments. The mountain of Ahuna Mons is invisible. The complex geology revealed by Dawn's cameras, the brine deposits in the ancient basins and the young dome structures, is compressed into a single point of faint light moving slowly against the background stars. But the processes are still running. The radioactive isotopes in the rocky core are still decaying, the brine is still percolating, the sodium carbonate crystals are still accumulating, slowly, in the fractures beneath Occator. Ahuna Mons is still standing, slightly lower than it was a million years ago, as viscous relaxation slowly flattens its slopes, but still unmistakably there. The asteroid belt does not need witnesses to continue its work. It has been doing this work for 4.5 billion years without anyone watching. The fact that there is now a species watching, cataloging, measuring, sample returning, orbit calculating, spacecraft sending, is a development so recent in the timeline of the belt's existence that it does not even register as a rounding error. The first human being to understand that the asteroid belt exists has been dead for less than 2 centuries. The first spacecraft to enter the belt intentionally, Pioneer 10, which crossed the inner boundary in July 1972, did so less than 55 years ago. In a belt that formed 4.567 billion years ago, 55 years of observation represents a fraction of time so small that expressing it as a percentage requires more decimal places than are useful. And yet, what those 55 years of spacecraft observations have produced, combined with the telescope observations that preceded them and the meteorite analyses that continue alongside them, is a transformation in the human understanding of where we came from and what the solar system is made of that would have been unimaginable to the astronomers who named these objects in the 19th century. They knew the belt existed. They did not know it carried the building blocks of life. They did not know one of its objects might have a subsurface ocean. They did not know the bright spots. They did not know that the material locked inside the dark, featureless asteroids of the outer belt contains molecular precursors of every protein and every living cell on Earth. They simply knew there were rocks between Mars and Jupiter, and they named them after goddesses and heroes and mythological figures because naming is what humans do when they find something in the dark and want to hold on to it. The names turned out to be right, in the way that some guesses are right. The harvest goddess, the goddess of dawn and growing things, the presider over the fertility of the earth, Ceres, Demeter, the figure at the center of the ancient agricultural cycle that made settled civilization possible. It turns out she was sitting in the middle of the material that made the chemistry of life possible. The mythmakers did not know this, but the name fits. You are drifting now in the slow current of the outer belt, and the cold is no longer something you are noticing, it is simply where you are. The rocks around you are moving in their long orbits, carrying their molecular cargo, doing the slow arithmetic of Keplerian mechanics that they have been doing since before the sun was old enough to have planets. The sun is small from here, but it is warm. Not warm in the way that warmth usually announces itself. Warm in the way that a distant light is warm, not felt on the skin, but present in the field of awareness as something that is there, steady, reliable, at the center of everything. You are in the asteroid belt. You have been here for the length of a night. You have crossed from the inner belt to the outer belt, descended to the surface of a dwarf planet, stood on a cryovolcanic mountain, held ancient rock in your hands, and followed the molecular thread from the early solar system to the chemistry in your own cells. The journey covered hundreds of millions of kilometers. It began with a bright spot in a dark crater. It ends here, in the cold and the quiet, with the rocks drifting in their ancient courses around you, and the sun small but steady ahead, and the long history of the solar system settling into the silence, the way dust settles in still air, slowly, completely, without resistance. Your breathing has been slow for a while now. Not because you are asked to slow it, because the scale of what surrounds you makes urgency feel like a misunderstanding, because there is nowhere to be more present than here, and here is a place where 4.5 billion years of patient physics have produced exactly the conditions that allow something like you to exist and notice them. The asteroids do not notice you, but you notice them. And that noticing, that quiet, half-conscious awareness of old cold rock moving through the dark on trajectories that will not change in any meaningful way for millions of years, that is what remains as the details of the journey begin to soften at the edges. The Kirkwood gaps, the Yarkovsky drift, the chondrules in the S-type matrix, the ion engine firing for 70% of a 7-year journey, the bright spots resolving from mystery into salt, the mountain that formed while mammals diversified, the amino acids in the dark rock that fell in Victoria, the water from a dying star locked in mineral grains older than the sun. These things are real. They are out there right now, in the cold and the dark between Mars and Jupiter, doing exactly what they have always done. The solar system does not require your attention to continue operating. The orbital mechanics run on the same equations they have run on since before the first living cell divided on the surface of the early Earth. Jupiter's resonances are still shaping the Kirkwood gaps. The Yarkovsky effect is still nudging asteroid orbits by fractions of a millimeter per day. The presolar grains in the outer belt asteroids are still carrying the isotopic signatures of stellar nucleosynthesis events that happened before the sun was born. None of this pauses when you sleep. All of it will still be there when you wake. You carry that knowledge with you now into whatever comes next. Let the silence of the outer belt be the last thing your mind holds tonight. Not a thought, not a question. Just the fact of all that patient rock, all that ancient chemistry, all that cold and quiet space, moving in its long, slow circles around a small, warm star. The star is still there. It is always still there. And the rock drifts, and the orbits hold, and the molecular cargo of the solar system's oldest material rides through the dark in silence, carrying the chemistry of life through a belt of fragments that never became a world, but which, in carrying that chemistry across the billions of years to the third planet, made it possible for worlds like this one to exist at all. Everything you heard tonight is real. The asteroid belt is out there right now. If this story reached you tonight, a like and a subscription to Quiet Science at Bedtime means more than you know. The notification bell ensures the next journey finds you when it's ready. Good night.